In this video, we are going to be getting into atmospheric pressure, what causes atmospheric pressure, but really the underlying, we are now into our second unit of the course. The underlying concept that we're really getting to using atmospheric pressure to get to it is the energy of particle motion. What does the energy of particle motion have to do with atmospheric pressure? Well, that's what this video is about. We know from before, from previous classes and such, if I take an object and I put some energy in it to get it moving, I'm going to take this little football, if I throw it, that has a certain amount of energy of motion, which we call kinetic energy. There's an equation. We're going to only use the equation qualitatively. We're not going to plug in numbers into this. But the equation for the energy of motion, and let's just look at it, what it means. Ke for the kinetic energy, or energy of motion, is equal to 1/2 the mass times the velocity squared. So that is what, so how much energy does a particle in motion have, or an object in motion? It depends on the mass and how fast. If I throw this football just kind of weakly, it doesn't have a lot of energy. So energy is an ability to make things happen, to make change. If I'm going to try and knock something over with this football and therefore cause a change, I need to give it some energy. And I would have to, if I throw it lightly, it has a little bit of capability to knock something over, right? So it has a small energy. If I take this thing and really just chuck it and throw it really hard, then it has more energy because I increased the motion. The other thing I could do to have more energy, what if I took, instead of this football was made out of some really, this is a like styrofoam thing, really heavy football. So it's made out, or like a shot put. And I'm just going to just throw that thing. Now it has a lot of mass. So it has more mass. And if it's moving faster, it has more energy of motion. Now, instead of these big objects, we're really interested in the energy of particle motion, little objects. So let's think of a gas. And we're going to use air. And we're going to do particle model. So one thing I know about gases, if I draw the particle model of a gas, I would say it's, particles that are spread out. In fact, it's even more spread out than that. So a lot of space with some particles, but I know the particles aren't just hovering there, right? They're not just hovering around. Even in very still air, in this room, the air is not really moving. In very still air, we know at the particle level, there's this random motion. So they're bouncing all around. So even if it's completely still air, there's all kinds of motion at the particle level. And we can see that. And so this model, the atomic model of matter, works for that. If I take this cologne, and let's see, what is it? It's white musk for men. And I'm going to spray it that way, away from me. Give it a couple sprays. So I gave them initial velocity going that way. What happens, in fact, even now I can smell a little bit, but what happens through time is, even though I sprayed them going that way, I will smell the cologne coming this way. Somehow those particles that were going that way wind up, at least some of them, coming back towards me. What I would like for you to do, normally if we were in the classroom, we would pause, we'd do some discussion, group discussion, and maybe make some whiteboard models. But for now, if you can just pause the video momentarily and think about, well, wait a minute. Particle was going that way, the particle of cologne. What caused it to turn around? And so pause the video for a second and think about it. And then we'll talk about what the reason is. So if you say, well, what caused it? And so I've seen all kinds of things within the classroom. People say, well, somehow, it grabbed onto one of these and pulled this way, or all kinds of things. But let's say this, I'll color it in. That's a particle of the cologne. Of course, it was a spray mist, but it vaporized and became, ooh, now I'm really smelling that cologne coming this way. So it was going this way. Why did it not just keep going that? And it didn't actually take a U-turn and come back. It got knocked back, right? So it's going this way. What's going on? I've got the air in this random motion, all kinds of it. So some air particle comes along, boom, knocks into it, gets it going a different direction. So what's going to happen to that particle? It hits this way, this way, this way, this way, this way, this way. We call it Brownian motion. And so it's moving in all kinds of different directions. Eventually, some of them are going to make it this way. An analogy I like to use is if there's a concert, a wild concert we're using, and there's mosh pits within there. I've been to those concerts, but I've never gone into the mosh pit. But so there's a big mosh pit going on within the concert. And I see someone, I'm at the edge of the mosh pit, and I see someone on the other side, and I say, hey, I want to go say hi to my friend over there. And so I step into the mosh pit. What happens? Well, before I can get to my friend, I'm not going to be able to make it straight across. Someone's going to knock into me one way, and then knock into me another way, and then knock into me over here. And so I'm going to go into all kinds of different random motion. And so that is what causes actually the particles to diffuse. So that cologne I spread started that way, but it got collided with gajillions of different times every second within all kinds of different directions. So that's what causes the particle to turn around, and that's what we call it diffusion. If I put some cologne in this area, due to the random motion and collisions of particles, eventually it will diffuse throughout the room. I have another setup here, and let me get this water cold. Put ice in there to cool it down. So on here, on this beaker, I have a hot plate, so I've got a lot of hot water. And now I'm cooling this one down to get it nice and cold. I'm going to give it just a second. So what I'm going to do is, let's look at the diffusion of food coloring. I got two different dyes. I've got a red dye, red hot, and blue for cold. I think I've got that water cold enough. I'm going to take the bigger chunks of ice out. And I'm going to try and add about 3 drops. In each one. And then I look at what happens, and so we can see, and I'll bring the camera in a little closer. We can start to see what's going on. Try and bring it around this way. Whoops. What happens is, in the hot water, that actually the dye has now spread completely around. In the cold water, it's moving, but not nearly as fast. So what I see is that food coloring spreads out and diffuses throughout the beaker of water much more rapidly in the hot water. Let me turn this off now. And carefully get that hot water over here. So in the hot water, it moves, the food coloring diffuses much more rapidly. Why? And this is one of course, the particle model of matter helps us to understand, well, I know that the energy of motion of particles increases with temperature. So in the hot water, those water molecules are moving all around really, really fast, and they're colliding and colliding, colliding. So this diffusion happens much more rapidly. So as the temperature increases, the particle motion increases. The kinetic energy of the particles increases as I increase the temperature. In the cold water, even though it happened much more slowly and still not completely diffused, the slower motion, they're just not kind of moving around as fast, right? So they're a little bit more mellow in there, and all the collisions are not as energetic. And so the motion, that diffusion, does not happen as fast. So this, we're going to really get into some of the detail and being able to represent this. How would I show hot versus cold? And let's just do a quick particle model on that. Liquid is random, right? And over here, same liquid, still random. What actually happens, we don't have to detail that now with that hot motion. So if this is hot and this is cold, all that extra energy of motion here actually opens up some tiny little gaps within the water. So cold, I'm going to show shorter arrows, right? So the length of the arrow is going to indicate something about the motion. If that's cold water, then what's hot water? Longer arrows, right? More kinetic energy of motion. Cold versus hot. And so those are the kind of things that we'll be working with in showing our particle models, and now in this case, really getting into the energy of those particles. We begin with the kinetic energy of particles, the energy of motion of particles, and we're also going to get into the potential energy, the energy of the arrangement, based on the arrangement of particles. Okay, I have another demo, something for us to consider. So what does all that have to do with atmospheric pressure? If we take a phenomena like sipping water through a straw. So if I've got a glass of water, and of course we do that all the time, sip through a straw, but we would say, how is that possible? When we think about it, wait a minute. My mouth's up here, the water's down there, and without me somehow reaching down and pulling the water up, I'm able to bring that water up to my mouth without actually being in contact directly with the water until it gets there. How is that possible? How is it possible for me to pull water? I'm not actually not pulling it, but it seems like I'm pulling water up through the straw. And a little activity we could have done, what if I had a straw, and this we can call it a straw, a piece of tubing, and I went up to the second story of a balcony outside the science building. Could you sip water, and there's a bucket of water down at the floor, could you sip water through a 2-story straw and bring it all the way up, and the bucket's way down there, and I got this big old long straw? Can you pull water up? And it turns out you can. It's really difficult to do that, but you can pull water up. Let's look at what's going on in a straw. Here's my straw. Of course, I got a liquid down here. I've got liquid inside the straw. There's air outside. And there's gas particles, air particles inside the straw above the water level. So there's air out here and air there. What happens when you're sipping through the straw? What are you doing? You expand your lungs, and the air rushes into your lungs and out here. Now, if you'd say, well, what happens? They're saying, well, somehow as the air comes up, it's bringing water with it. That's not actually what's happening. The air does not get pulled up. The water is not pulled up through the straw. It's getting pushed up. How is it getting pushed up? All of these particles of air, and they're tiny, infinitesimally small particles. And so you say, well, one little ding, how that's not going to push water. Yes, it will. And so I use the analogy of a bug's life. In the bug's life, the tiny little ants were getting bullied by the grasshoppers. And what did the ants realize? They said, well, wait a minute. There's a whole lot of us. If we all get together, we're really, really strong. And that's the case with air. We're used to, we've evolved to be in this thing, in this atmosphere. So our structures are able to hold up against the constant bombardment of air particles. The air in the atmosphere can push this water level down. If I pull the air here, which was pushing down, but now it's gone, that push isn't going. What happens? The water will rise up. It won't rise up all the way because there's this thing called gravity trying to pull it down. So it's a battle between the push of the atmospheric pressure and then gravity trying to pull down. In the Google document, there is a picture of the old school mercury barometers. Right now, to measure atmospheric pressure, we use electronics. But there's an old school mercury barometer. And what it shows, and I'm just going to show some of it, because this gets to our units for atmospheric pressure. What are our pressure units going to be? A common unit in the United States is pounds per square inch, but we're going to use that almost not at all, right? So when you fill a tire to 35 psi, pounds per square inch, we won't use that. In a mercury barometer, why mercury? Why did they used to it? Well, of course, it's toxic, so we don't use it anymore. But why were they using mercury? It's a very dense liquid. Therefore, the gravity pulls pretty hard with that. And so it can only rise so far because of its density. The barometer is the little bucket of mercury that's exposed to the atmosphere. And so the atmosphere is pushing this column. Above the column of mercury, we say it's a vacuum. In chemistry or in science, a vacuum does not mean a vacuum cleaner. So it doesn't mean a suction. It means an absence of particles. So there's no push here. There's no push from gas particles because we've taken them all out. If I bring this down and I take one of these mercury barometers and I take it to the sea level, the pressure at sea level under normal atmospheric conditions, right? Sometimes a high pressure system comes through or a low pressure system comes through, but under normal weather conditions, that column will rise up 760 millimeters. 760 millimeters in height. And so at sea level, so if I draw a little ocean, right, and I take that barometer to sea level, the pressure is enough. I'll draw a little fish in here. The pressure is enough at sea level to push a column of mercury up 760 millimeters. So one of our units for pressure that we'll use is called 760 millimeters mercury. And we'll have some pressure stuff in the Google Doc attached. 760 millimeters mercury at sea level. So this unit, millimeters mercury, is the amount of pressure that can push a column of mercury up 1 millimeter. 760 millimeters at sea level. The other common unit for pressure, for gas pressure, or atmospheric pressure, or any gas pressure that we'll use is I'll say, well, you know, what about another unit? Let's create a unit based on the atmospheric pressure at sea level. And so let's say at sea level, normal weather conditions, let's just call that 1.0 atmosphere, or ATM. So our units that we're going to use, millimeters mercury and atmosphere for gas pressure, and there's another one, it's called torr. So some guy named Torricelli came up with a lot of this stuff. And so if you come up with big things in science, sometimes you can get it named after you. So millimeters mercury is often called torr. And when we get to AP chemistry, we're going to call it torr. So millimeters mercury is 1 torr. But also probably the most common unit pressure is atmospheres. How many atmospheres of pressure? If I take air and compress it really big, I can move it above 2, 3, 4 atmospheres of pressure. So we're going to work with that. So energy of particle motion, all that particle motion, what does it do? It collides with surfaces as they're bouncing around and they're hitting the surfaces. What does that push on surface? It's causing pressure. What causes atmospheric pressure? The collision of particles of air on a surface. And so we're going to expand with this, work with the gas properties, and this is kind of, we're going to use the properties of gases to really explore this energy of motion of particles.